Strong and weak acids and bases is a topic that we have covered before. We covered it back when we were talking about electrolytes. However, it has particular relevance to the acids and bases topic, so we're going to go over that again just as some revision, but hopefully all of the things that you hear in this video will be familiar from what you did in semester 1. The 2 dot points in the 2B syllabus that relate to this is describe and explain the difference between strong and weak acids, including a number of examples, and describe and explain the difference between strong bases and weak bases, including a number of examples. So just as a reminder, the strength of a substance is based on the proportion of particles that either ionize or dissociate, remembering that ionise is a process that happens to covalent molecules, and dissociation is a process that happens to ionic substances. If 100% of the particles either ionize or dissociate, then we say that that is a strong electrolyte. So it could be a strong acid or it could be a strong base. If there is partial ionization, meaning that it's actually a reversible reaction, then we say it is a weak acid or a weak base. The strength has a number of effects on the properties of a solution. The strength will affect the number of ions that appear in the solution, so therefore it will affect the electrical conductivity. If you had a strong acid and a weak acid at the same concentration, the strong acid is a better conductor of electricity because it has more ions in solution. Another change is to reaction rates, and that's due to the different concentration of H+ in a strong acid compared to a weak acid, as is the H+ or the hydronium ion if you're using Bronsted-Lowry theory, which is able to react with substances. So for example, if you've got 1 mole per litre of hydrochloric acid, which is strong, and 1 mole per litre of acetic acid, which is weak, and you added magnesium to both, the hydrochloric acid would react faster with the magnesium than the acetic acid would, because there is a higher concentration of ionized protons in the hydrochloric acid solution. Now back in this syllabus dot point, it did mention a number of examples which you need to be able to include in your descriptions and your explanations. So I wanted to just quickly go over how you'd write the equations for these types of substances being ionized in water. Once again, this is revision, this shouldn't be new material, but you might actually understand it a bit more this time than you did the first. So we're going to start with our strong acids. And these are the ones that fully ionize. There are 3 strong acids that you need to know. They are hydrochloric acid, nitric acid, and sulfuric acid. In each of these equations, I've shown the Arrhenius theory, I've shown it ionizing to produce a H+ ion, and the other substance, which is basically the leftovers once you remove the H+. Note that for the sulfuric acid, I only did 1 H+ being removed. For more information about the ionization of sulfuric acid, check out the next video on polyprotic acids, which deals with this type of substance with 2 ionizable protons. You can also have some weak acids, and these are ones that partially ionize. Examples of weak acids, the number 1 example which frequently appears is acetic acid. Acetic acid undergoes a reversible reaction, which means that these products, the hydrogen ion and the acetate ion can react together again to form acetic acid. So you never have 100% of these products. You always have some of these molecules and some of these ions in solution. Another one that's said on the syllabus is the phosphoric acid. So a reversible reaction to produce dihydrogen phosphate ion. Some other examples of weak acids, I won't do equations for all of them, but it also includes H2CO3, which is carbonic acid, and it includes various ions that have a hydrogen in them, including hydrogen sulfate, hydrogen carbonate, dihydrogen phosphate, and hydrogen phosphate. Sorry, it's meant to be -1, not -2. This one's -2. The easy way to remember what is a weak acid, though, is to remember the strong acids, and the weak acids are the ones which are not strong. Because these are reversible reactions, don't forget it includes a double direction arrow. Onto the bases. The strong bases are substances that fully dissociate, and it includes the group 1 and group 2 hydroxides, with group 1 and group 2 referring to groups on the periodic table. So examples of group 1 and group 2 hydroxides would include sodium hydroxide, potassium hydroxide, and magnesium hydroxide. Each of these substances will fully dissociate when dissolved in water. And because this is a one-way reaction, I'm using a single direction arrow. The weak bases are ones which partially ionize, the most common example for a weak base will be the ammonia ion. For the ammonia ion, I can't show it with the Arrhenius theory as I've done with the others, because ammonia can't be explained with the Arrhenius theory. So I'm showing it with the Bronsted-Lowry theory instead, with the ammonia gaining a proton and the water losing a proton. It is a reversible reaction, hence partially ionizing, because the products will react again to form the reactants, and you'll never get 100% of either products or 100% of reactants as they continue to react until they form an equilibrium. A second example that you need to know for weak bases is the carbonate ion. When you dissolve a substance like sodium carbonate in water, there's actually two steps that happen. The first step is dissociation. So when you dissolve Na2CO3 solid in water, it produces sodium ions plus carbonate ions. And at this stage you might be thinking, well, how come this isn't classed as a strong base? Because this is obviously a one-directional arrow. It occurs 100%. The reason why it's a weak base is due to the second reaction that occurs, and this is the part that actually makes the solution basic. The second part is the ionization of the carbonate ion. So this carbonate ion, which was produced by dissolving sodium carbonate, it undergoes a reaction with water, similar to the way that the ammonia did in the previous equation. And during this reversible reaction, the carbonate acts as a proton acceptor to become hydrogen carbonate ion, and the water has once again lost a proton, so it becomes hydroxide. So in both of these equations, one substance, in the first one it was the ammonia, in the second one it's the carbonate, is able to react with water in a reversible reaction to produce hydroxide and the conjugate acid of the original substance. Because it is a reversible reaction and it never occurs to a full 100% extent, they're both classified as weak bases. Some tips for you to remember. Basically, you need to know which things are strong and which things are weak. For the acids, HCl, H2SO4 and HNO3 are strong. All the other acids are weak, and you should show them with reversible reactions when they ionize. For the bases, it's the group 1 and group 2 hydroxides that are strong, and other bases such as ammonia and the carbonate ion are weak. Make sure that you include the correct arrows with your reactions, as often that is actually being marked, and if you put a single direction arrow for something that should be reversible, you can lose marks in tests.